This video is about the logic of hypothesis testing. Our first example will use a form of a non-parametric test, in this case a one-sided exact permutation-based test. Our goal is to test whether the central values of two groups differ. This slide presents the raw data. The mean of group A is 3, whereas the mean of group B is 38. In practice, I'd suspect that the 99 is a symbol for a missing value, although for a laboratory measurement it might represent a value that's too numerous to count. Let's assume that B represents an active intervention and that A represents a control. We're only interested in using B if it increases the outcome on average. In other words, we're looking at a one-sided test. Framing the question in terms of means would require us to deal with the 99 as a possible outlier, whereas framing the question in terms of medians would not. Transforming the data into ranks would be a reasonable thing to do for either measure of central tendency and would lead to a non-parametric test. Loosely speaking, the null hypothesis always states that there's nothing going on. Depending on the statistical test to be used, this idea might be operationalized by saying the means of the two groups are identical, the medians of the two groups are identical, something similar. To perform a permutation test, first transform the data into ranks. Now the group means are 2 and 5, respectively. Then notice there are exactly 720 possible permutations of the data, at least if I've counted correctly. This slide illustrates 3 of the possible permutations. Please note that the first 3 data points always correspond to group A, and the second 3 data points always correspond to group B. Key insight in developing a permutation test is to recognize that if the null hypothesis is true, each of the 720 permutations of the data is equally likely to occur. To perform a hypothesis test, what we need to do is determine whether the version of the data that we actually happen to observe is extreme. Importantly, what we're checking is whether the observed data are extreme relative to what would be expected were the counterfactual assumption of the null hypothesis to hold. If the data are consistent with the null hypothesis, we conclude that the group means don't differ. On the other hand, if the data are extreme in comparison with what we would expect under the null hypothesis, we conclude that the group means do differ. This can be stated more precisely, but I won't bother to do so. It turns out that asking whether the data are extreme is difficult to operationalize. Instead, we can get at the same idea by asking whether the test statistic is extreme. Here, the test statistic is the difference between the group means. The observed value of the test statistic is +3, a positive sign indicating that the mean rank from group B exceeds the mean rank of group A. P-value is defined as the probability, assuming the null hypothesis is true, of observing a value of the test statistic that is as extreme or more extreme than the one you observed. Here the possible values of the test statistic range from -3 to +3. Assuming that I've counted correctly, the relative frequency of values with +3 is 36 out of 720, or 5%. The histogram will be symmetrical around 0, with large relative frequencies near the center of the distribution, and smaller relative frequencies near the tails. This histogram is a visual representation of the sampling distribution of the test statistic under the null hypothesis. There are no values that exceed +3, so the probability that the observed data is as or more extreme than +3 is 0.05. In other words, the p-value is exactly 0.05. This slide draws the distribution of the test statistic, assuming that the null hypothesis is true. The shaded area represents the p-value. To perform a parametric test instead of a non-parametric test, the sequence of steps is very similar. The null hypothesis continues to be that there's no difference between the group means. The additional assumption is usually that the group means are normally distributed with identical variances. The data aren't transformed into ranks. The test statistic is the difference between the sample means, divided by a function of the pooled variance and the sample sizes within the groups, and it has a t-distribution for small samples, which approximates a normal distribution for larger samples, which we'll assume from now on. Importantly, if the overall underlying group means are identical, the sampling distribution of the test statistic will be a standard normal distribution. This information is enough to fill in the acceptance and rejection regions. For example, the cut point for differentiating between a data value that's statistically significant, p equals 0.05, and one that isn't, will be approximately 1.645. As drawn, the test statistic is the signal-to-noise ratio, and the test statistic is on an absolute scale. If the test statistic is instead taken to be the difference between the sample means, in other words, the signal only, the cut point separating the acceptance and rejection region changes from 1.645 to 1.645 multiples of the standard error of the difference between the sample means. This slide has exactly the same structure as the previous one. The only thing that changes is the 1.645 is replaced with 1.645 standard error multiples. Continuing the example of a parametric test, how then is a power calculation performed? We begin by specifying whether the test is one-sided or two-sided, and also the type 1 error rate of the test. In other words, what magnitude of p-values are required for statistical significance. This is enough to derive the benchmark value of the sampling distribution of the test statistic that differentiates between values that are statistically significant versus values that aren't. In the previous slide, that benchmark value was 1.645 standard error multiples. Here it's simpler to specify the test statistic as the difference between group means, rather than the difference divided by a scaling quantity. The only role of the null hypothesis is to derive the benchmark value. In general, what you have to specify to perform a power calculation depends on the statistical test. Here you must specify the underlying means for groups A and B as well as their standard deviations. I won't be discussing how you as a statistician can assist investigators in actually specifying these quantities. For any given sample size, above information is sufficient to derive the sampling difference for the difference between the sample means, assuming that the alternative hypothesis is true. This distribution is normal. The mean is the difference between the underlying group means. The spread of the distribution is based on the standard deviations and the sample sizes. Now draw the sampling distribution of the test statistic under the specific alternative hypothesis that the underlying group means differ, as described above. Append to this picture the benchmark for statistical significance. Please note that the sampling distribution test statistic is centered not around 0, as was the case for the null hypothesis, but instead is centered on the difference between the population means of the two groups. The power of the statistical test is the area of the distribution that's contained within the rejection region, that is, the shaded area. How is this important and useful to a practicing statistician? Well, our clinical investigators need sample size calculations performed, but they're often mystified by them. If you can create some version of this argument that successfully explains power calculations to your clinical colleagues, they need not be mystified any longer.